Bismillahirrahmanirrahim. Assalamu alaikum viewers. Hope the previous two videos you might have watched would have helped you a lot in understanding the concept of the integration. Now here in this video we are going to understand the integration of exponential and logarithmic functions with the help of few examples that I've collected for you. So here I prefer to write here first of all the basic formulas of exponential and logarithmic functions. So you see the integral of exponential function is exponential itself plus some constant, because you know that integration is the antiderivative process. So whatever the function you're having through the derivative, if you just try to integrate that function, you're going to get the original function back. It's like that. So we have if you have studied your differentiation, there you might have studied that the derivative of exponential function is exponential function itself. So if we just try to find out the integral of exponential like that, so you are going to get your exponential function back. So you see, integration is going to cancel out its anti-process, which is the derivative process. So it is going to cancel out its effect. What is left is the function. Okay, so this is the function so left, and it is equals to the integral of this, right? So that's how we just try to understand. This is the case that is going on. Now if I just say that derivative of my log, either it is a log of any base other than your Euler number, or it is a natural log having base Euler number, we are not that's not the case. In both cases the derivative is going to be the reciprocal of that of that log variable. Okay, so it's like that. So if I just say what is going to be the integral of this 1 upon x, the integral of this 1 upon x is definitely ln x or log x itself, right? It's like that. So you see, these two formulas we are going to understand here in this video, and with the help of its relative examples. Okay, you might be thinking right now that she has just mentioned exponential integral and the integral of the reciprocal of the particular variable that we are discussing, which is equals to your log plus some constant. What is going to be the integral of the log? Of course, integral of all functions exist, so of course the integral of logarithmic function also exists. So naturally, or basically or primarily, we cannot find out the integral of logarithmic function, okay, directly. In order to find integration of this function, we have to take the help of our by parts rule. So by parts rule is something that we are going to discuss in our 4th video or upcoming video. So over there we are going to study it deeply with the examples. So here I'm not discussing this case. Okay, I'm just focusing on those questions in which there is an involvement of integration of exponential function, or integration of the reciprocal of the variable that is involved, or reciprocal of the variable of the function that is involved. Okay, so let's go ahead and pick up a couple of examples and try to understand the concepts. So let's begin. Okay, now here's a nice question number 1, and here they have just given us a function in which there is an involvement of there is a variable which is in the denominator and cannot be further simplified. So this is basically a rational function, right? So you know that those functions in which the denominator contains a variable that cannot be removed or cannot be completely erased out after applying the maximum simplification. So once the denominator variable exists, such kind of function or such kind of expression, they're called the rational expressions. Okay, so here you are having a rational expression, and we need to find out here, and its graph is also mentioned here nicely, you can see, and in part number 1 we need to find out the coordinates of the maximum point and the minimum point, which are assigned by the variables p and q here. Okay, so you know that what are the minimum points? Minimum points are actually the points which are actually situated in the valley, and maximum points are those points which are at the peak point of the hill, or in other words they are trough of the pulse, or they are crest of the pulse, right, of the graphical pulse, like that. So how we are going to find out the x coordinate and y coordinates of point P and Q? So for that purpose, what we are going to do, in derivatives, you know that once we just try to draw the tangent on these extremas or stationary points, the tangent on these points are going to be completely parallel to our x-axis. So of course the slope of these tangent lines is going to be 0, right? So we know that derivative actually helps us in determining the slope at of the tangent line drawn at a particular point, right? So what we do in order to find out the coordinates, we first of all find out the derivative of this function y, and then we will equate it to 0 to find out the coordinates of the x coordinates of these extreme points, right? So what we do, I just say that let this equation or this function is represented by equation number 1, and I'm going to differentiate both sides of this equation with respect to the original variable, that is x. Original variable is actually that variable which is actually involved in the making of that equation, right? So this is the independent variable, so we are going to take out derivative of this thing. So you know that derivative of our x is going to be 1, and the derivative of our 1 upon x is actually x power minus 1. The derivative of this thing we can find out by using xn formula of the derivatives, right? So it is going to be simply 1, and this is going to be nx n minus 1. So it is 1 minus 4 upon x squared. Okay, so this is it. So that's what you say, this is the tangent, or this is the slope of the tangent line. Okay, now you know that the tangent lines on the extreme points are having slope 0 because they are parallel to the x-axis. So how about if I just equate this equation number 2 to 0 and find out my relative x coordinates of these points? Okay, so let us find it out here a little. So this thing is actually equals to 0. So 4 upon x squared equals to 1. So it means that x squared is equals to 4, and I just try to take out square root, so it is giving me plus minus 2. So the 2 points, or the 2x coordinates that I'm having here of my x and y points, they are, I must use a different color here for you, they are, this is minus 2 and this one is plus 2. Okay, now the next objective is to find out the y coordinate of my p and and y coordinate of my q. So what I do, I just pick up my original function 1, equation number 1, and I just substitute my x values there one by one and get the corresponding y coordinates, right? So I'm just doing it because it is the part of the question, though it's not the part of our topic, but it's part of the question. That's why I'm doing it. So you see, for x equals to 2, y is equals to 2 plus 4 upon 2. So it's going to be 2 plus 2, 4. Okay, so you see my p point, or the coordinates of my point P, are 2 and 4 respectively. Similarly, I just move on here and try to find out my q y coordinate. So for x value minus 2, y is going to be minus 2 plus 4 upon minus 2. So it is giving me minus 2 plus minus 2 on cancellation, of course. So it is giving you minus 4. So q coordinates are minus 2 and minus 4. I hope it's clear. And these the x coordinates are definitely going to help you in your next part, so because we need to find out the area of each shaded region here. So they're just asking us to find out individual shaded regions area, so they're not asking us to find out the total area of the shaded region. So you see, first of all, we just find out area of this region, this narrow one, and then area of this region, the broader one by one. So this is it. Now let me just remove this, avoid little messy work. Okay, now we are going to find out area of our shaded region. This is the part number 2 here. So what to do, I just call this area as my region A and this as my region B. So area of region A. Okay, it is going from minus 4 to minus 2, and f of x times f of x dx. Okay, so now you know that f of x is actually your y, alright, and y is x plus 4 upon x, right? So minus 4 to minus 2 x plus 4 upon x dx. Okay, so if you have just watched my first video, then this finding out, in which we discussed the area, how to find out area under the curve, over there we have discussed all these limits concepts very deeply. So I hope you are not going to encounter any further trouble in understanding this process. So okay, so we just now apply our integral on each term of our expression like that. Now you see that integral of your 1 upon x is ln x plus c, as we have just said. So we just use that formula here, and here we just used xn formula, so it is going to be x1 plus 1 upon 1 plus 1 plus 4 times integral of your 1 upon x is ln x. Okay, minus 4 is going from here to here. Alright, we keep on moving like that. So it's going to be, you see, it's 1 upon 2, I just take it out, and this is x squared, which is going from minus 4 to minus 2 plus 4 times. Now I can apply this 4 inside, because it is going to help me out in further solving. 1 upon 4, and I can apply my limits here. So it's going to be minus 2 square minus 4 square plus. Now if I just try to apply my limits value directly over here on x, then you can see it is going to be ln of your minus 4. That is of course giving you math error on the calculation on your calculator, or if you just try to use a log table, it's going to give you infinity. Okay, it's going to be undefined. So you see that log of your negative values is undefined here. So we have to avoid this case. So for that purpose, that's why I said that I just have to bring my 4 inside over here, and then I'm going to use the major formula of my log of my polynomial, in which the log of xn is equals to n times log of x. So here the case is written like that, so I can make a back substitution and I can write it like this. Okay, So how about if I just write my 4 ln x in the form of ln x power 4. Okay, now the case is going to be resolved very nicely. So we just move further down and we just keep on going our calculation. So it is going to be minus 2, this is 4 minus 16 plus, now we just apply here our log values. It's going to be minus 2 power 4 minus ln minus 4 power 4, just like that. So it's going to be 1 upon 2 minus 12 plus ln of your negative 2 power 6 power 4. It gives me what it gives me, minus ln of my 256, because minus 4 power 4 gives me 256. Okay, now you can activate your calculators now, and this is going to be minus 6 plus ln 16 minus ln 256. It is going to give me, let me open my calculator, there you go. So it is ln of my 16 minus ln of my 256. It is giving you minus 2.772, so I can write up to 2 decimal places. That is more than enough for me. Okay, so it's going to be minus 2.77, so it is giving me minus 6 minus 2.77, so it is finally giving you minus 8.77. and you know that area is actually something that you calculate always positive. If area is telling you nothing but a magnitude, okay, so this negative sign is going to be omitted, and because just like you see that length is always positive, so you omit or you neglect the negative sign. So that's the thing that we are going to do in the case of our area as well. So we just say that area is equals to 8.77 square units. Okay, so we see that here, where is our figure? Okay, so the area of this region A is 8.77 square units. The same process we are going to apply with respect to the limits going from 2 to 5. The same function we are going to use. We apply the same process, and we will get our area of region B as well, likewise. So let's do that thing as well. So that's the case, and as I have already solved the integrand for you, so I'm not going to repeat the steps again and again. And I will just write it directly here for you, going from 2 to 5, and this is going to be ln x4 2 to 5. Okay, it's going to be 5 square minus 2 square plus ln 5 power 4 minus ln 2 power 4. Okay, so it's going to be half times 25 minus 4 plus ln of your 5 power 4 is, I guess, yes, it is 625 minus ln of your 2 power 4 is 16. Okay, so we just do it, the remaining steps over here. So here area is equals to 21 by 2 plus, and we just ln of 625 minus ln of 416 can be calculated here. So ln of 625, sorry for that, minus ln of your 16. So it is giving me 3.66 or 3.67 on rounding. So it is 3.67, and this is going to be 10.5 plus 3.67, and when I add 10.5 in it over here, 10.5, so it is giving me 14.2 14.16 approximately 14.2. So 14.2 square units is the area of region B, and you see it is greater than our region A area because our region A was a little narrower than our region B, so of course its value is higher than that of our region A. So I hope the concept is clear. Now we just move on to our next question. Now here you see this, the next question. You can see here a figure is already drawn here, a graph is already shown here. It's the graph of the exponential function. Okay, so if you want, I can enlarge the size if you want to. If it is okay, so you see here the coordinates of point A, B and C are given to us. So it is 0, 5, A is ln 5, 0, okay, B is ln 5, 5, and so on. So we need to find out the area of the region OABE. So OABE is actually this region. We need to find out area of this region in the first part, which is bounded by this curve, this red curve, the x-axis, the y-axis, and the line AB. Okay, so this is it. So we need to find out the area of this region. Okay, so we simply use our basic formula of finding out area with the help of integrals. You see the x value is going from origin to point A, right? So the limits going from origin to ln 5, right? Y dx. So y is your f of x, which is equals to your exponential x. Okay, so, and you know that integral of exponential x is exponential itself. So exponential itself, you are now going to apply your upper and lower limits. So ln 5 minus e power 0. So you know that exponential e is the anti-function or inverse function of our natural log, okay, because natural log is the log of base e. So whenever these two functions are combined together, they are inverse of each other, so they will cancel out each other's effect. So what is going to left is the value of the log over here. You can further confirm it through a calculator that if I just write here exponential with its power ln 5, so you see ln and e are going to cancel each other's effect, and what is left here is 5. Okay, so that's the concept. So we just write 5 here minus an exponential power 0 is 1, so it is equals to 4 square units. So the area of the required region OABE is 4 square units. That's it. Now we come to the next part of this question. It says that after that, once you find the area of OABE, find the area of the shaded region EBE, this purple shaded thing. We have to find out the area of this region. Okay, so EBC. So how we do, you see that this is the full complete rectangle. If I find out area of this rectangle and I just subtract area of the region that I have just find out over here, this one, I'm going to get the area of the purple region, right? So that's the concept we are going to use here. So you see this triangle OABC is having width equals to ln 5 and having length equals to 5 units. Okay, so you see that the length from the width from here to here, it is equals to ln 5, okay, and the length from here to here is equals to, you see, it's 5 values, so it is 5 units higher in length. So so the width or I must say the area of this triangle OABC area of our shaded region is going to be equal to area of triangle OABC plus area of a region OBAE. Okay, OABE. That's it. Alright. So you see this is equals to what? This is equals to 5 multiplied by ln 5 plus 4. I'm sorry, I have to subtract and I'm adding it. My bad. So it's getting subtracted. Sorry for that. So this is it. So 5 times ln 5, this is length and this is breadth. That's what I'm talking about. So it is equals to what? 5 multiplied by ln 5. This is giving me 8.047. So it is equals to 8.047, and I'm going to subtract my 4 from it. So it is giving me 4.047, of course, right? So it's going to be 4.047. So if they haven't specified that, write your answer up to 2 decimal places or up to 2 significant figures. If there is no such case, you can write up to 2 decimal places or 1 decimal place, totally your choice. So I just prefer to write my answer up to 2 decimal places after rounding. So it's going to be this. So that's what my answer is. Okay. Now let's see the part 2 of the same question here. Let's see what it is asking us to do. Now you see in part 2 it says the graph of this exponential function, which is already given to us here, it is transformed to the graph of y equals to ln x. So you see we have to draw the graph of our ln x here on the same graph provided to us. And then after looking at these two graphs of exponential and logarithmic functions, we are going to find out what kind of transformation it is showing up. Okay, so for that purpose, you see, of course you cannot draw your ln x graph directly. You need to pick up a couple of values and then try to sketch the graph here. So you see the scale or the axes which are so provided to you, both are positive. Both x and y values are positive. So you see, pick up the positive values of x over here, at least 3 to 5 values of x. So here you see you are provided here. This is gonna be 1, 2, 3, 4, 5, something like that. Because you see this is actually ln 5, and ln 5 is 1.6 something. Okay, so it is of course between right at the right side of your 1.5. Okay, so it's quite clear that these values that I have just mentioned here, they are 1, 2, 3, 4, 5. There is no doubt here. Okay, so this is it. Now we just pick up values from 0 to 5, try to construct the table here of ln x and try to draw the curve of it. Okay, so I just pick up my nice values and I just try to find out. So you see, ln of x, ln of 0 is of course infinity, it is undefined. Ln of over 1 is 0. Ln of over 2 is going to be 0.7. You can check it from your calculator, it's from there. Ln of 3 is 1.1 approximately, ln of 4 is 1.4, and ln of 5 is 1.6. Okay, so these are the values here. And here on the y-axis, this is something 1, 2, 3, 4, 5. It's like that. So now I'm going to pick up the points, and just on the basis of an idea, I just try to highlight my points here, and I would like to extend my y-axis a little down just for explanation. Okay, now you see at x value 0, y is at infinity. So actually at x value 0, what is going to be my y, I have no idea. So I just try to draw here an asymptote here, and I just keep on moving like that. Okay, so that's what the behavior is. So at 1 I'm having 0. Okay, at x value 2 I'm having 0.7. so you see this is your 1. 1.5 is actually in the mid, and 0.7 might be over here. so it is over here. Okay, at x value 3 I'm having 1.1, so 1.1 is probably here, so that's what I'm going to draw. At 4 I'm having 1.4, so you see this is your 1.5, a little below 1.5 is going to be your 1.4, so that's what the point is, like that. And 1.6 is going to be above your 1.5 here, so it's going to be a little above. So you see, from infinity I'm going, and I will start moving my curve. I have to move in a freehand way, but I hope you cooperate. So this is going to be the curve. You see, this curve, if I just try to monitor only the part from here to here, you see this curve and this curve, they are actually reflection of each other with respect to the line y is equals to x. If I just try to draw a straight line y is equals to x, you see at x value 0 y is also 0, at x value 1 y is also 1. That's going to be the point. So you see, this is going to be the axis of reflection, and with respect to this axis of reflection, you can notice that this red curve is the reflection of this black curve. So exponential curve is actually reflection of my logarithmic curve. Okay, if you just further you can check through your graphic calculator, though it's not allowed in your A levels, but just for authentication I would like to mention here a graphic calculator. You see, y is equals to, if I just draw here my exponential curve, well, like that. So you see, this is the exponential curve, and in the question, just the segment from here to the value 5, only this segment from here to here, that is provided to us, okay, in the graph, in the question. And similarly, if I just try to develop here my logarithmic curve, so y is equals to my ln x, you see ln x, this green curve and this red curve, you see they are exactly reflection of each other with respect to the line y is equals to x. Okay, so this line, this purple line, is actually the axis of reflection. So you see, if I pick up this point is actually the reflection of this point. Okay, so they are exactly right in front of each other. So this is it, that's what the behavior is. So you see the transformation of this red curve and this black curve, they are reflection transformation. Okay, so this is it. So once they ask you to describe the transformation, so it is a reflection transformation, no issue in that. So once it is a reflection, so of course the area that is so occupied by your red curve, the x-axis, the y-axis, and this line, whatever this shaded region is having the area, the same region is going to be over here. The same area is going to be occupied by this region that I have just shaded over here at the bottom level. So you see, this is it. So the area of whatever the area of this shaded region is going to be the area of this B region. I'm calling it B. Okay, so part 3 says that using your answers in part 1 and 2 or otherwise, show that the area of the region or area of the curve ln x going from 1 to 5 is equals to this. Okay, so as area of purple region is reflection of area of this region B, so as we have just calculated over here, that area of this shaded region was 5 ln 5 minus 4, so area of region B is also going to be 5 ln 5 minus 4. Okay, so you don't have to do any kind of calculation here. What you just do, you just write a nice statement that as region B is reflection of the shaded region above, so that's why whatever the answer of the shaded region is, it's going to be the answer of the region B as well. Okay, so it's like that, simple as that. Just make a nice English and you will make it. So okay, now we just move on to our part A and B of subpart A and B of part 4. You see here ln 1 upon 5 is equals to integral from 1 to 5 of ln x cube is actually 3 times ln 3. Here we are just using a log characteristic, so it is 3 times integral of 1 to 5 ln x dx. So you see this is equals to what? We know that integral 1 to 5 ln x dx is 5 ln 5 minus 4, so it is going to be 3 times 5 ln 5 minus 4. That's going to be the answer of your part A. Similarly, if you talk about your part B answer, so ln of 3x means 3 getting multiplied with x, of course. So you are going to use here the formula of log of product of two values, as you have studied. So log of product of two values is actually the sum of the log of those individual values. Okay, so we are going to take the help of this, and ln of 3 dx plus integral of ln x dx. Okay, I hope it's clear. So as you know that ln 3 is a complete constant value, so just take it out, and at the place of integrand you're having nothing but 1, and now you simply apply a nice integration. So it's going to be ln of 3 times x going from 1 to 5 plus ln integral 1 to 5 ln x we have calculated already in the previous part. This correlated, it is 5 ln 5 minus 4, so it's going to be 5 ln 5 minus 4. We just apply here the upper and lower limits, and it's going to be 4 ln 3 plus 5 ln 5 minus 4. You can either keep your answer as it is, or you can write your answers in terms of decimals as well. If they specify that you should mention your answer up to particular decimal places, then you have to show it. So otherwise you can leave it as it is if it's not mentioned there. So on solving, I just got that it is 8.44. That's gonna be the answer, and that's it. Okay, so this is it. Now let's see the next example here. Okay, now here you go, the next example. You see here in the denominator you are having an irreducible factor, so you cannot remove the variable from here. This is a rational function. So how about if we just apply here our u-substitution, and then we are going to see its picture, how it looks like, and on that basis we are going to integrate it. So if I just say that though I can do it directly as well, but u-substitution is much better to use here. So u is equals to 2x plus 3, and I differentiated both sides with respect to my original variable. Okay, so du by dx is equals to derivative of x is 1 plus derivative of constant 3 is 0, so it is giving you 2. So du is equals to 2 times dx. As you can see here, we are not having any 2 here in the numerator. So what I do, I just shift my 2 over here, and I simply shift my dx on the other side. So at the place of my dx, I would write half du. Okay, now we are going to change the limits. So if your x is -1, then your u is going to be 2 times -1 plus 3, which is 1. Okay, and if your x is going to be 3, then u is going to be, simply substitute the values of x, and going to be 6 plus 3, that is 9. Okay, so this thing tells me that this original function with respect to x is now transformed into an integrand involving u. So it is now going from 1 to 9, 1 upon u times half of du. Okay, the constant half is going to be written outside the integral as according to the rules. So now what is now here is 1 upon u du. Now you're having a reciprocal function, so it is going to be equals to your ln u du, and ln u and nothing else. Excuse me. Okay, and now you can see this half is going to be moved inside if I want to do, though I can do it without it as well, but later on indeed I have to apply it. So how about if I applied it in the beginning? So it's going to be u power half, okay, going from 1 to 9. In other words, it is ln under root u going from 1 to 9. Right, now you just apply the limits. So it is ln under root 9 minus ln of your 1. So it is going to be ln 3 minus ln 1, and ln 1 is 0. So simply the answer is going to be ln 3, and that's how it is solved. So you see, actually what was happening, we were determined to find out the area under the curve of this function moving from -1 to 3. Okay, and thus it comes out to be ln, its value comes out to be ln 3. That's how we do. So you see here in this question, both u-substitution and logarithmic function involvement was there. So it takes 2 major steps, and we just got the answer. So actually we have just calculated this, the graph of our function 1 upon 2x plus 3. So this is the reciprocal function indeed. So we were determined to find out the area under the curve starting from this point, from -1 to over here, from this point to plus 3, and 3 is over here. Okay, so from this point to this to that point, we have to find out the area under that curve bounded by the x-axis. And that was equals to your ln 3. So I hope it is clear. Now we see our next question. Okay, now this is it. Our next question is also in the form of our rational function, and we have to show that this function is going from -2 to x, and its area under the curve is going to be equals to this. That's what we have to bring. Okay, it's a 2009 June question. Okay, so we are definitely going to use our u-substitution here. So you see that integral is going from 2 to 6, and I just write this numerator 6 constant outside. It's x upon 3x minus 2 times dx. So what I do, I just assume that let my 3x minus 2 is equals to u. Okay, I just differentiated both sides. Now I'm doing it a little direct. So you see du by dx is equals to derivative of this thing is equals to 3. So I come to know that my du, that my dx is going to be 1 upon 3 du. Okay. Similarly, we are going to change our limits as well. So if my x is equals to 2, then my u is going to be equals to 3 times 2 minus 2. So it's going to be 6 minus 2, that is 4. And if my x is equals to 6, then my u will be equals to 3 times 6 minus 2. So it's going to be 18 minus 2, so that is 16. Okay, so this thing reveals that now my function, which was this, is going to be transformed in terms of u. So it is 6 times integral going from 4 to 16. And this is my u. Now you see, I have to write, what should I write over here in the place of my x? So you see, I pick up this equation, and I'm going to transform this equation keeping x as a subject. So it'll be equals to what? It'll be equals to u plus 2 upon 3. Okay, so it is u plus 2 upon 3. It's like that. This is your x, this is your u, times 1 upon 3 du. Okay, now what I do, I just transfer my this 3 and this 3 over here outside the integral. It's 4 times 16 u plus 2 upon u. Now I can apply my back substitution. I will individually divide both the numerator terms with my denominator u, and I'm going to get a simplified integrand, and then the job will get easier. So the area is equals to 2 by 3. Integral is going from 1 to 16, 4 to 16, and is going to be u upon u minus 2 by u plus 2 by u du. Okay, so it's what we call a back substitution. So once you take out the limit of your integrand, you're getting this thing back. That's why I call it back substitution. So it is now 1 plus 2 upon u du. Clear? Now we are going to apply the integral separately. So it is going from 4 to 16 du plus 2 times 4 to 16 1 upon u du. Okay, close the bracket. Now my area is going to be 2 by 3, and it's going to be u 4 to 16 plus 2 times ln of u 4 to 16. Now I can bring this 2 inside, and then I can apply my logarithmic property of my polynomial. So it is going to be ln u square. I can write it like that, 4 by 16, 4 to 16. So some nice relevant steps, and it's going to be 12 plus ln of 16 square minus ln of 4 square. Now we're getting closer. 2 upon 3, 12 plus, now ln of your 256, ln of your 256 minus ln of your 16. It is giving me 2.77, so 2.77 approximately. So it becomes 14.7. The 2 by 3 multiplied by 14.77. So we just go to the calculator again, and I'm going to add my 12 here. So it is giving me this answer, then I multiply with my 2, and then I divide it with my 3. So it is giving me 9.84. So that is my answer. But you see, I have to bring this thing equals to 8 plus 8 upon 3 ln 2, and I just forgot it. I just moved with the flow, and you see. So you see, at this step, I am not going to solve it and bring it into a decimal form. I have to bring the form that is mentioned in the book, in the question. So okay, so how about if I just try to multiply these terms? Now how about if I just write this 16 and 4 both in terms of my 2, so it is 2 power 4 whole square minus ln 2 power 2 whole square. So it's gonna be this gonna be 8 plus 2 by 3, and over here it is ln 2 power 8 minus ln 2 power 4. Yeah, so I don't need to write these values at the place of my power, so I just bring it back. So it is 8 ln 2 minus 4 ln 2, so it is equals to 4 ln 2, and now I'm getting my desired answer. So it is equals to 4 times ln 2, and on multiplication it is giving me 8 plus 8 upon 3 ln of my 2, and that was they were asking us to bring, and we just did that. So this is it. Okay, now let's see last example 5. Okay, so here they have again given us a reciprocal function, and they're asking us to find out the value of k for which this area should be equals to 1, and k is the upper limit here. So same process, you see, you can you see previously I just resolved the denominator expression in terms of by using my u substitution. Okay, now how about this time I just solve this question without u substitution? Okay, there should be some alternative also available. Okay, so with respect to the marking scheme, so if it is of low marks, then of course you're not going to use u substitution, it comprises too many steps. So here this is my, it's k. Okay, my k looks quite weird, so this is it. And you know that just assume that as this is a linear expression in the denominator, it cannot be further reduced, cannot be further simplified, cannot be removed, so it is considered to be one variable. Okay, so just assume that it is 1 upon x, okay, or 1 upon some variable, a simple variable. So it is equals to your ln of that variable. Now what you do going from 1 to k, now in the denominator you are going to take the derivative of this 2x minus 1. Okay, this is the alternative of your u substitution. If you are not using u substitution, then you just apply the formula directly, and then in the denominator you are going to differentiate this expression. Okay, so it is going to be simply 2 once when I take out the derivative. So ln times 2x minus 1 upon 2 going from 1 to k. Okay, and I just take out this 2 outside, and I just say that it is equals to my ln times 2k minus 1 minus ln times 2 times 1 minus 1, so this is it. Okay, so it is 1 upon 2 ln 2k minus 1 minus ln 1, and ln 1 is 0, we know that, so it is going to be vanished. Ln of 2k minus 1. So I can also write this thing as ln of 2k minus 1 power half. I can write in this way as well. Alright, so you see that this thing was equals to 1, so entirely I can write it like that, that this was equals to 1. Now what is going to be, how I'm going to find the value of k here? I know that my ln 2k minus 1 is equals to 1. So how about if I apply my exponential at both sides, because I know that the inverse of my natural log is the exponential value, right? So I just apply exponential at both sides. So it's going to be written like that. These values are going to be placed at the power of the exponential. So this is it. Now here exponential is going to cancel the effect of my natural log, and what is left here is under root 2k minus 1 equals to e. Now I just take square at both sides, so it is going to be e squared. Now I just move here. So k will be equals to e squared plus 1 upon 2. So this is going to be the value of the k. And that's it. I hope it's clear. So this video was a little bit long, almost close to an hour, but I just tried my best to cover the basic questions involving the particular exponential and logarithmic functions. I hope if you would just watch this video to the end, it is definitely going to help you out. And inshallah, I'll see you then in the next video, where we are going to discuss by parts. Thank you for watching. This was Maria Khan from mymathsclub.com.